power electronics control related to the power of photovoltaics, wind energy, so on. All right. So that is where I come from. I will give you the contents of my presentation first, right? We're going to go through the introduction and background, what is electrical drives, which is very much related to the power electronics itself. So I'm just going to how the power electronics is related to the electrical drives, the first part of the presentations, and why we use power electronics, right? I'm sure some of you have never heard of what power electronics is. Okay, if you in UTM, the course on power electronics is offered in the final year, which is the 4th year, is it? Yeah, 4th year. So 3rd year, sorry. Sorry. So some of you don't know what is power electronics. So I'll try to explain it as simple as possible. And then we're going to see how this power electronics is related to the motor drives. And then the heavier part is on the modeling and the control of the induction machines. Okay. We are going to deal with mathematical equations, modeling, and then we see how using these, manipulating these mathematical models, we'll develop the control systems which is used for the high performance control of induction machines, which is the field oriented control, FOC, DTC, and direct torque control and predictive torque control. I will probably don't have time to go through all this control, but the slide is there. You can refer that later. Probably I will just go pick one of them depending on the time, okay? I'll probably pick a DTC, which I think is very much related to what is going on at PT Semen. All right. And then I'll just briefly give a hardware implementation on how we implement this high performance induction machines control, some experimental results, and also the past and the previous research activities that we conducted at UTM. If you have any question, you can interrupt me anytime, right? Okay. So what is the drives? Let me just give a brief definitions or general definitions of the drive first. It is basically a systems that you use to perform a specific task. Like, for example, moving a load, lifting a load, something like that. Right? And then if you perform this mechanical task, then you have to have a prime movers, okay, the source of where your motion is coming from. We call that prime movers. If the prime movers is coming from the electrical motors, okay, we call it electrical drives, right? Which means that the source of the motion doesn't have to come from the electrical drive. It can come from the hydraulic drive systems, can come from the diesel engine and so on, right? All right. But if the prime mover source is coming from the electric motors, which can be of many types, what I'm going to be presenting here is just one type of the motor, which is induction motor. Then we call it electrical drives, right? Which means that if the electrical motor is an induction motor, then that drives is what we call the induction motor drives. And the trend is nowadays is to more and more of the electrical drives are shifting towards the use of power electronics, right? You can see, for example, I give a simple example, of the air conditioning system, right? Air conditioning system in our home or even here. Previously, before the applications of power electronics, how do you control the temperature? You control the on and off of your compressor, right? If the temperature gets too cold, then you turn it off. System will turn it off. If it is a little bit warmer, then you turn it on again. You control it using the on and off, which is very inefficient because every time you turn on your motor, okay, motor drives, then it draws a lot of current, and it will take some time before it settles to a steady state temperature or steady state speed. All right. So instead of controlling that on off of the compressor, nowadays we see the air conditioning system are using what we call the inverter control, which is basically power electronics. Okay, so instead of on-off, turning the compressor on and off, you control the speed, which can save a lot of energy. We'll see that later on how this is actually achieved. All right, that is just one example. Another example is in the in your refrigerator, for example, which is nowadays are basically using the power electronics, which is also the inverter, to control the temperature instead of turning on and off the compressor, right? So the trend is to use power electronics system. So let me just give you definitions of the drives in terms of the diagram now. All right, we have the power electronics converters, which is the center of that definitions there. Then we have the input power, which is typically unregulated. Okay, the voltage, which can be AC or DC source, but typically it is unregulated, which means that you have no control over it. Okay, it is unpredictable. It can come from the wind, for example, wind generator, or it can come from the photovoltaic, which is unpredictable, unregulated. And then you have to use this unregulated power to run the load. In this case, is the example is on these three-phase induction machines there, which means that what power electronics converter has to do is to regulate the unregulated power into a power which is suitable for the load. Let's say, for example, that your input is coming from the battery for electric vehicle applications, then your induction motor is an AC machines, all right? You're required to produce a sinusoidal voltage or current, which means that your power converter will modulate the DC into a AC source, all right? And that is taken care by the controller, which gives or provides the switching signals to the power electronics. Okay, probably not sure what is the switching signals. I will talk about that later. Right. So we have the load, mechanical load here, which is connected to the three-phase induction machine. There is a mechanical coupling there. And we have a controller which generates the switching signals to these power electronic converters. In some cases, you need to regulate the control variables, which can be, for motor drives, can be either the speed, the torque, or the position. All right. So you have to have a feedback, right? You have to have a feedback, which basically nowadays they try to eliminate sensor as much as possible. For example, if you are controlling torque, then you don't install torque sensor to your drive because that will reduce the robustness of the system, all right? If you are controlling the speed, you don't install speed sensor to your drive systems. Try to avoid that because first, that is too expensive, increase the cost, and then reduce the robustness because you have to make sensor in the harsh environment, for example, all right? So what we do is we estimate the torque and the speed from the voltage in the current. There is a different type of research area that is going right now in motor drives. So, okay, so that feedback is basically, in this case, the voltage, the current, and sometimes the speed. But then again, I say the speed can be sometimes is eliminated, but in fact, on the other hand, it is estimated using the voltage and the current of the motor. So the drive system itself is interdisciplinary. It involves a lot of areas. You have the motor drives, you have the power electronics, you have the control, you have the electronics part, you have the power system parts, you have the machines part, okay? Several research area, which is expanded. I think now it is going to be saturated soon. And then it is small compared to the previous drive system, which does not use power electronics, for example, which uses a Watt-Leonard configurations, which use multiple machines. Flexible, you can just change the controller or the algorithms of the control of different source. For example, you can have the same power electronics converter for AC source or even DC source, all right? And then you can change that. If you change the load, then you can just change the control algorithm that controls your power converter. It is very flexible. So let's talk a little bit more about this power converter, since it is the heart of a modern electrical drive systems. Those who have taken power electronics then probably know this. Power electronics converters are basically composed of the passive elements, which are capacitors and inductors. Okay, and then we probably have high frequency transformers, okay, not a normal transformer that you see to reduce the loss. And then we probably, the important part is we have the semiconductor devices. These are the three basic elements that compose power electronics converters, right? And these semiconductor devices is operated not in its linear region, but rather in its cut-off or saturated region, which means that it just operated as either on or off, all right? And by doing so, which means that if you look at the power dissipated in this on switch or semiconductor device, then if it is fully turned, then you have zero voltage. In practice, of course, there will be a saturated voltage of the transistor, all right? And then when you turn it off, then the current is going to be equals to zero. But in practice, there will be a small leakage current present, right? But this leakage current and saturated voltage is going to be very small. So ideally, we know that the passive element has zero loss ideally, but in practice, of course, there will be resistance and associated with the capacitor and inductance, as well as for the high frequency transformer. But ideally, the efficiency is going to be 100%, which means that whatever input that you put to your power converters here will goes to the output, 100% efficiency. But even though if you include these losses, which I said earlier, the efficiency is still going to be higher. Can go as high as above 90%, okay? 90 or 95%. So that is the reason actually why people are using power electronics, which is because of its high efficiency, right? And why it is high efficient? Because we are operating the semiconductor device in its saturated or cut-off region, which is operated as a switch. You know, if you operate the semiconductor device in its linear region, you have a voltage and you have a current, and that contributes to the losses in the semiconductor device, right? So by operating it as a switch, which is a fundamental concept in power electronics, then you basically reduce the losses. The reason why we use power electronics can be divided into an energy scenario. We look into the energy scenario and also the global warming. If you look at the electricity generation in 2017, which I don't think will be much different nowadays, that most of the energy or the source for generating the electricity is coming from the fossil fuel, okay, which is coal, gas, oil, a little bit on nuclear, which is can be considered as clean, but it is very dangerous. We all know that. Then we have the renewable energies, which is coming from, for example, photovoltaic, wind, or hydroelectric can also be considered as renewable, right? So it is predicted that over the years, for example, I took this from one of the papers, which predict that in 2020, 2200, the coal will be depleted. All right, even we know that, okay, because it is non-renewable, renew this energy, so sooner or later it will be depleted. All right, and then we have the oil, the gas also will be depleted. And the problem is how we can do this to flatten the curve. What I mean flatten is the curve is to prolong this usage or the availability of these sources. All right, which is not a good choice actually, because if we flatten the curve, then we're still polluting the earth. All right, we just prolong the use of this the usage of this fuel, but we are still polluting the earth. But anyway, if we want to flatten the curve, then what we can do is to use a high efficient energy, obviously using the power electronics. All right, that will reduce the energy consumed, therefore can somehow give a longer period of time for the usage of this fossil fuel. Another smart choice is to move the fossil fuel. All right, but instead we use the renewable energy. Okay, even if we opt this option, we'll still need power electronics, because as I said, this renewable energy is unregulated, it's unpredictable, We need to regulate the power to suit the load. All right. And the only way we can do to improve or to give the highest efficiency to, to minimize the losses is to use the power electronics at the moment, right? So anyway, anyway, whether we are talking about conserving the energy or using the renewable energy completely, we need power electronics. So what is so bad about this burning of fossil fuel? We know that if you burn fossil fuel, then you produce CO2 or carbon dioxide, okay? These extra productions of carbon dioxide, which is outside the nature, which is we know is produced by the trees, okay, by us, is not good because it will increase the temperature of the okay. Naturally, CO2 is produced by us, by breathing, by us or by the trees. Then that is good because CO2 trap the heat, so that avoiding a too cold temperature of the earth. Okay, just nice. Okay, but if the CO2 is too much, then more and more energy will be trapped. That will cause the increase of the temperature of the surface of the earth. Okay, if CO2 is trapped in the atmosphere of our earth, then more and more energy will be, more CO2 will be trapped. So the temperature, the overall temperature of the earth will be increased. But if you look at the study conducted by NASA, since the last industrialized era, the temperature has increased 1 degree Celsius, which is a lot, okay? Which is a lot. If it is, we consider only the natural productions of the CO2, then we can see that the green, projections of the CO2 productions there. But if we include the CO2, which is produced, man-made CO2, which is also known as the greenhouse gas, then the temperature is since the last industrial era by 1 degree Celsius. And this is not good because if the earth, then what happens is that you will melt the ice and you will increase the sea level, right? Which is one of the reasons why Indonesia is shifting the capital from Jakarta to Kalimantan. I think one of the reasons, all right? It is predicted by 2100 that 0.6 meter of sea level would increase, will cause the warmer oceans, more unpredicted weather, more evaporations, extreme weather, place where before there's no drought, it's experiencing drought, or place where previously was experiencing the whole year drought, now is becoming greener, for example. Okay, it's unpredictable. All these things is what we call the climate change, all right, which is caused by the warming of the earth. You can see the relationship there between that, what is happening there. It all started by the greenhouse trap gas. What is scary is that you have a closed loop path here, okay? The greenhouse gas is melting the snow, and earth absorb greenhouse energy, and then there has a positive feedback, okay? Positive feedback of producing more greenhouse gas. So this is very dangerous, and in order to avoid or mitigate this, we have no choice but to use power electronics at the moment, right? So that is the reason, okay, the strong reasons why we need to save the energy, avoid the burning of the fossil fuel, and use power electronics in order to save the earth. All right, now let's go to the next part of the presentation, which is the power electronics and motor drives and how these are related. As I said earlier, the relationship between the development of the motor drives are very much related to the development of the power electronic, right? It all started in, when the first power semiconductor device, which is known as the SCR, silicon control rectifier, was invented by Bell Laboratories in the United States in 1958. Okay, which means that with the inventions of these semiconductor devices, I'm not sure how many of you are familiar with the silicon control rectifier, SCR, where the silicon control rectifier or SCR can be controlled on and off, okay, by providing the gate signal to this SCR. So it's basically just a switch. With the inventions of the SCR, a device which is called the inverter is also invented. Okay, inverter is a device where you can convert a DC voltage into an AC voltage using different techniques such as pulse width modulation and so on. All right, so before this invention, the variable speed applications, motor drives, where you need to control the speed, for example, in the elevator systems, all right, trains and so on, uses the DC motor because there is no source, variable AC source, which is available at that time before the inventions of the inverter, right? You can control the induction motor by using the auto transformer, but that is going to be very inefficient, right? So we have no choice. If we want to apply the we want to have the variable speed applications, then we have to use DC motor. But then after the SCR or the inverter was invented, then more people are shifting from the DC drives to an AC drive, because after the inverter was invented, then the DC voltage can be converted into a variable frequency, variable amplitude AC voltage, right? Which means that we can use induction machines, which is previously used as a constant speed applications, to control the speed now, all right? But that is not good enough, because at that time, the technology is only available on how to control the frequency and the magnitude of the AC voltage, all right? Which means that for high performance applications like elevator, lift, electric trains, electric car, and so on, are still dominated by these DC drives, right? The AC drives, using the inverter with the available technology at that time, which can control only the voltage and the frequency, the magnitude of the voltage and the frequency, is only applicable or applied to the low to medium performance applications such as pump, fans and so on, which does not require an accurate control of the speed. But then in 1970s or in late 1960s, I think, a German professor invented what is called the field-oriented control, which is basically a breakthrough in induction machine or AC machine control. It transformed the control of the AC machines, induction machines, into similar to what we have for the DC machines. All right. Those of you who are familiar with DC machines know that. How do you control the DC machines? You just control the armature current, right? If it is a separately excited DC machines, then you fix the flux, the field flux, and then you control the torque by controlling the armature current, which is very simple control. But that is not possible before FOC was invented to apply that to the AC drives or AC motors, okay? But with the inventions of this FOC in late 60s, early 70s, then it is also possible now to apply induction machines to a high performance applications, which is the reason why we see, previously the lifts are controlled using DC motor, okay? But nowadays, all lift, I think, is controlled using AC motors. And also the electric trains, when we first installed LRT in Malaysia, it was using DC motor, but nowadays all DC motors are being replaced with AC motors. Why we use AC motors? Because it is robust, cheaper, lighter, does not require maintenance and so on. If it is a DC motor, then it is not easy to build, expensive. Then you are heavier, the inertia is higher. It requires regular maintenance because of the brushes and the commutator. So, but it was introduced in 1970s, but later it will take probably about 10 years before it can be commercialized. The theory was invented in 1968, if I'm not mistaken, by a German professor. But when he first invented this OC, there is no processor which is fast enough to implement the control. All right. Using FOC, you estimate the torque and the flux in real time. which require a very fast processor. But it was then become commercialized probably about 10 years after that, all right, which is in 1980s. And then at the same time, also in 1986, another control technique, which is again a breakthrough in AC drives, was invented. DTC stands for director control, which I think is, which I was told, used by P.T. Semen in his Keelan drive system. All right. Director control DCC is the proprietary of ABB, which is a company in Germany. Okay, and it's if you go to the ABB website, and you can see that it actually supply the drive systems for the cement industries. Okay, it uses, I think it is ACS 200 for medium voltage range of motor drives. All right. So what is good about DTC is that it is simpler compared to FOC, does not require frame transformation. But the main drawbacks of DTC is that it has large torque ripples. Talk about that later on how to improve that. A lot of people are doing research on how to improve on the ripples of the DTC, and we also have done that before ourselves in our lab. And then it was introduced in 1986, DTC, but it was commercialized in 10 years later, which shows that, it will take some time for the industry to trust your new control techniques, right? For example, FOC was introduced in 1970s, but it was then commercialized in 1980s. Okay, DTC was introduced in 1986, was then commercialized by ABB as a proprietary to that in 1996, 10 years. And then after that, we can see nowadays that the high performance applications are shared between FOC and DTC, and a lot of DC motor drives, which has been used before, has been replaced with this AC motor controls, okay, which has the advantages of robustness, cheaper, easier, cheaper, and does not require maintenance. Okay, for example, in the cement industry, the old technology in the Keelan drive, which requires a high precise torque and speed control, uses DC motor. Okay, but I think nowadays all of the Keelan rotary drives, use the AC motors. Okay, can be either a dual motors or single motors. All right, we'll talk about that later when we look at on the applications of the drives in the cement industry. Okay, so about 40 to 50% of the electrical energy are used for the electrical drive, right? Used for the electrical drives, and the applications of the drives nowadays can be divided into two types, which is the fixed speed and variable speed. All right. At the moment, this data is taken a long time ago because I cannot find the latest up-to-date data on the the percentage of constant speed and variable applications. This is taken a few years ago. 75% constant speed, 25% of variable speed. I think nowadays it is probably 50-50%. All right, probably 50% of constant speed and 25% of variable speed of the of drive systems using the variable speed applications. All right. What is a constant speed? The constant speed is simply you have an example of this is you have a three-phase voltage supply, which comes from the utility, and then you directly connect that three-phase voltage supplies to the induction motor, right? And we know that the frequency for system in Malaysia as well as in Indonesia is 50 hertz. Which means that you cannot control the speed of the DC motor, of the induction machines. If you connect it directly to the utility supply, can only run close to the synchronous speed, right? The synchronous speed for for synchronous for 50 hertz system is 1,500. There is a mistake there. It is not 157 TRPM. It is actually 147 TRPM. You cannot go higher than the synchronous frequency, right? For 4-pole machines, you produce a synchronous speed of 1,500 RPM. So you have to minus the sleep frequency of the induction machines. Then the machines can be, maybe operated at rated speed of 1,470 RPM. Okay, not that 1,570 RPM. It's a mistake there. All right, but that's it. So you have a fixed speed, all right? So the variable speed, on the other hand, is where you insert the variable speed drives, okay, in between the motor and the source. So you have a variable speed drive there, which is shown by that sophisticated box control here, which is fed, which means that the source from the utility is fed to your equipped variable speed drive first, and then from there, the output of the variable speed drive is connected to your motor, right? Which means that the input has a fixed frequency, whereas the output can have a different frequency and different amplitude. Okay, so you have a variable voltage, variable frequency, which means that the speed of the induction motor now can be controlled from the 0 to the synchronous speed. All right, that is the basic fundamental of difference between the constant and the variable speed application. So what is the big deal about using these variable speed drives? Save energy. Okay, not only because it is using power electronics, but the way that it is controlled will save energy. I'm going to talk a little bit more about this later. So if you save energy, then you reduce the CO2 emissions. You contribute, which means that you are contributing to the mitigations of the global warming, which is good. And then with using the variable speed drives, you can also control the starting torque. If you connect the machines direct online start, then at start, the machines will produce a very high torque, which gives, introduce stress to the mechanical parts of the system. All right. But however, if we use a variable speed drive, then we can gradually increase the speed, which means that we are reducing the mechanical stress. Therefore, we can increase the lifespans of mechanical parts. And then they require less maintenance, since mechanical parts are, the reliability of the mechanical part is increased because of that slow starting torque, for example, or starting current. And also, you can reduce the starting current, which means that you can use smaller ratings of your switchgear. All right. Because as I said, if you connect it directly, then you have a very large surge current at startup. And to reduce that surge current, if you use a variable speed drive, then you can gradually increase the current, which means that you don't have to design or size the switchgear, the transformers, based on the starting current, right? So it can be smaller size because of the soft start. Higher process quality and efficiency. Well, depends. You can control the process depending on the process flow, the inputs and outputs of the process. Depending, you can control it by controlling the speed of the induction motor. All right, of the variable speed, which means that you can actually match the productivity. You can increase the match productivity capacity by controlling the speed of for example, the back conveyor system. All right, and how, especially why we can save energy by using the variable speed drive. I'm going to just talk a little bit on how and why we save energy. Let's look at first on how the flow air is controlled using a constant speed. This is, for example, a blower or a fan, right? In which you have the input air here and you have the output air there. And then it is coupled to your motor drives. In this case, a constant speed, all right? Which means that the induction machine is directly coupled to the fan of the blower, and the machines is directly connected to the three-phase supply, 50 hertz. So it is a constant speed drives, right? If you buy a fan or a blower, then they will give you what we call the pressure, static pressure versus the volume of air characteristics, right? At a given speed, there is a certain value of pressure and the volume rate, all right? This is what we call the fan curve or the fan characteristics, which shows here that if you want to reduce the volume rate flow of your blower or your fan, then you have to increase the pressure, okay? Is going to be increased. This is, for example, can be done by controlling the outlet dampers of your blower. Okay, if you reduce the opening of your outlets ports, then you are increasing the pressure, the static pressure, right, of your of the fan, which means that if you block the flow of air, then you are reducing the volume the volume flow. The volume in terms of the cubic meter per time, minutes or it can be second. Okay. Now, let's say, and then there is also what we call the system curve. A system curve is a relationship between the static pressure and the volume flow of the system, which means that a system which is include everything. It includes other components such as dampers, filters, and obstruction. And it is not given at a constant speed. Can be of a of different speed, which means that for a given flow rate here, then you require a certain static pressure there, right? Which is not a constant speed characteristics. But here, the fan curve is a constant speed characteristics, which means that the fan is running at a constant speed. You want to reduce the flow rate, then you have to obstruct the fan opening, which means that the pressure is going to be increased. All right. Now, let's say that the applications require that we reduce the volume flow, all right, to Q2 instead of Q1. How are we going to do that if we're running at a constant speed? We cannot change the fan characteristics because it is running at a constant speed, right? What we can do is change the system curve. And we do this by changing the outlet dampers, for example. If you change the outlet dampers, then you require higher pressure in order to produce the same rate of flow. All right, you change the system curve. You cannot change the fan curve, which means that to reduce the volume flow, then the pressure P2 now is going to be higher than P1, which means that you require more energy to run that. All right. Now, this is not good because this is based on constant speed. Alternatively, we can use a variable speed, which is, again, we insert the variable speed drives in between the two, between the supply and the induction motor. And then what we can do is that we can remove that dampers. Okay, we don't need that dampers anymore to control the flow rate. And we can therefore remove the curve here. All right. But let's say that, for example, we are still requiring, a reduced flow rate of Q2. How do we do that? Well, now we don't change the system curve. Okay. Previously, we changed the system curve by adjusting plate with the dampers, the outlet dampers or the inlet dampers. But now we remove that. So we change the flow rate by changing the speed, which means that if we change the speed, then you change the fan curve, right? At different speed, then you have a different fan curve or fan characteristics. All right. So if you adjust that properly, then you get a new reduced flow rate of Q2. But now with a lower pressure, static pressure, which means that you save energy, right? By instead of playing around with the dampers, outlet dampers, or inlet dampers, for that matter, then you are reducing the flow rate by reducing the speed, okay? Reducing the static pressure requirement, therefore reducing the energy usage. In fact, it was reported by ABB that if you use this type of control, the cement industry previously is controlled using, for example, the slip ring induction machines, where you dissipate the energy into the rotor resistance, but you replace that with this variable speed drives. You can save the energy by as high as 20% of the energy used in the cement industry, right? That is what is reported by ABB. I'm not sure whether it is true or not. But anyway, what is inside that variable speed drive then? Okay, you was thinking of what's inside that actually, all right? So what is inside that? This is a basic structure of the variable speed drive. It contains several power electronic converters, all right? We have the input here, which is coming from the utility. And again, we have the output here, which is going to the induction machines, for example. Okay, in between there is the power electronic converters. The first stage is convert the AC voltage to a DC voltage first. Okay, a variable unregulated control of AC voltage is first converted to a DC voltage, and then the second stage is to convert that DC voltage to a AC voltage. Right, this is a two-stage conversion process. That is a more sophisticated converter, which uses the matrix converter, which I don't think is yet. I'm not sure whether it is available in the market, but I don't think ABB supply that. which directly converts the AC to AC without have two conversion stage, right? And the control is more sophisticated, right? And at the middle there, you can see that there is what we call the crowbar circuit, which is necessary because the diode rectifier here is only flow power in one direction. It's a unidirectional current device, okay? Which means that the power can only flow from the source to the load for this rectifier, okay? From source to the load. If you do a braking in your machines here, then the mechanical kinetic energy is going to be converted to electrical, right? So the kinetic energy has to flow back to the source. If this only allows a one direction flow, then most of the kinetic energy, therefore, is going to be dumped on the capacitor here, okay? Because you cannot have a flow of energy power from here to the source. Then during the braking, where the kinetic energy is converted to electrical, then the excess energy is going to be dumped to the capacitor. Okay, if too much energy is dumped to the capacitor, then your capacitor voltage will go higher and higher. Then you have to release that excess energy by using this crowbar circuit, which just basically switch that, turn on that transistors on and off the transistors, which means that the energy is going to be released through that crowbar circuit. All right. This is a typical structure of the variable speed drives. A more expensive, which I think is ACS 2000 from ABB, they use an active transistors here at the front end. Instead of using a diode rectifier, they use transistors, which means that the power can go back to the supply. So you don't need that, that crowbar circuit there. It saves more energy, obviously, right? So if you replace that diodes with the transistors, then it is called the active rectifier. Then the power can actually goes back to the supply. But if your braking is not that frequent, then installing this expensive active front end converter is not worth. Okay, so for example, if the braking is produce only a small amount of energy, which is not worth to be saved, then investing on the much higher converter is not good, right? But if the braking is, almost always happens, and you have a lot of energy to save or during the braking, then it is worth to install or to invest on the active front end converter. Okay, so some converters has the diode rectifier, which does not allow power flow back to the supply. But some converters, some the variable speed drives has the active front end here, which uses the transistor in which you can, fed back the power to the supply. All right. If it is not fed back to the power using the diode, then the power has to be dumped to this capacitor. That we call that dynamic braking. All right. If the power is fed back to the supply, then we call it regenerative braking. All right. So you can look at on specifications of the drive systems, whether it is a regenerative braking or otherwise. Now, the control of the induction motors can be divided into two types. In general, what we call the scalar control. The scalar control is developed based on the steady state model of the induction machines. You probably have seen the model before, which is a per phase equivalent circuit of the induction machines. You have a leakage inductance, you have the magnetizing inductance, you have the stator resistance and rotor resistance. I'm not sure whether you are familiar with that, but that is basically a steady state model. That model does not valid under transient states where the speed and the voltage varies in real time, right? So the scalar control is developed using this steady state model, and the control frequency is on the magnitude and frequency. This is what I introduced you earlier, before the inventions of the field-oriented control. Okay, this is how the speed of the induction machine is controlled using the scalar control, which means that the applications is limited to the low and medium performance, fans, blowers and so on, compressor, which does not really require a precise torque control. All right, so it is relatively easy to control and obviously cheaper. Now, if you require a high performance control where you need to precisely control the speed and the load can change, unpredictably, and you need to control the torque in order to maintain the speed, then you have to use a vector control, right? Vector control is developed based on the dynamic model of the schemes, and it controls the magnitude and angle of the vector of the voltage and the current. So it's not a scalar quantities, it controls the quantity, which is the magnitude and the frequency of the voltage or the current. And it is suitable for high performance applications, relatively complex, right? Require a huge amount of computation power. You cannot use just a simple microprocessor to do that. You have to use, for example, the trend is to use the digital signal processor and the field programmable gate arrays, to implement this high performance control. It can be further divided into three types at the moment, which is available in the market. I'm not sure whether predictive control is available or not. But the first two, which is FOC and the not FOC in the bracket there, which is supposed to be DTC there. Field on control, FOC, direct torque control is DTC. And then we have a relatively new type of control technique, which is what we call the predictive torque control, or PTC. The control is on the model predictive control. Okay. If I have time, then I will talk a little bit on that. We have a research currently working on that. Few PhD students are working on that now and then. So let's look at on how this, I think the same diagram which is used by Prof. Wan previously, which we obtained from PT Semen, I think, website. All right, the process of the producing the cement, where the drives are required, especially on the variable speed drives. It's all over the process, actually, all right? Starting from the crushers here, which normally you use a squirrel cage induction machines. You don't require to use the variable speed here. All right, so typically you just use a constant speed. I'm not sure. Okay, constant speed. If you require a variable speed in which you can control the process of what is going in, what is going out, then you can use the scalar control instead of a high performance control. You don't need a precise torque speed control there. All right, the crushers for the crusher 1 and crusher 2, the power rating is about, I think, around a few hundred of kilowatts, right, for the crushers, for the crusher motors. And then we have the raw meal here, okay, which is used to reduce the size of the limestone into an acceptable size, which basically consumes the most of the energy, or the electricity is consumed in this two meals here, basically, or in fact 3 meals. We have the raw meal here, and then we have the cement meal here. Okay, and also we have the coal meal. I'm not sure whether the kiln is powered by the coal here. Is it? If you have coal, to increase to have that high temperature, then you most likely you most likely require the coal meal as well. So these meals consume a lot of energy. All right, we're talking about megawatts here. All right. So if you can save a small amount of, even 0.1 or 0.5% or 1% of energy there, it gives a lot, because of the high power involved here. All right. So that is where the variable speed drive can be used. One of them is in the raw meal. And then we have of course, to transport everything here from here, then you have the conveyor belt, again uses the drive. And then again, if you use a belt conveyor, then you need to control the speed as well, because the process flow, you require probably to reduce the flow, all right, rate. Then you probably need to control the speed of this belt conveyor as well. Now, and then it goes to the preheating process here before it is fed to the kiln, all right? The heat which is used for the preheater is coming from the recycle of the kiln rotary, I think, right? But anyway, the material is then fed into the kiln, where you increase the temperature. It can be as high as 1,500 degrees Celsius, and you have to mix all this together by keep on rotating the kiln drive. This is very important because the torque can be, unpredictable here. The load torque can be unpredictable, which means that you have to precisely control the torque and the speed. You cannot use scalar control here. definitely you cannot use, all right? Which means that previously this Keelan drive uses the DC motor, because DC motor you can control the torque easily by controlling, as I said, the armature current, for example. But when nowadays, I think most of the cement industry, including PT Semen, I was told by Dr. Imran, uses the direct torque control in the Keelan drive, all right, which gives you a precise torque and speed control. Reduce the stress on the mechanical parts, reduce the starting voltage, starting current, starting speed, and so on and so on. And it's not easy to control. Okay, but it is implementable by using the ACS 2000 drives systems from ABB. All right, which uses direct torque control. Then you have to cool down here. Then you have to the clinker, which is the production of the output of the kiln, which is called a clinker. You have to reduce the high temperature 100 degrees Celsius using the cooler fan here, which again sometimes need to be controlled. Okay, previously this cooler fan here in this to cool down the clinker is using the slip ring induction machines with a slip recovery, okay, to save the energy. But I think it is more and more of the cement industries are using the variable speed drives here, to control the speed of the fan. And you don't need the high precise torque and speed control again here, which means that you can use a scalar control. All right, scalar control. And then you have the final mill here. Okay, the final mill, which is what called the cement mill, to produce a smaller particles here. Again, here, it is good to use a variable speed drive, because that, depending on the input and the output here, then you can control the process by controlling the speed, right, of the mill or the grinder. So that is where basically the variable speed drives are required in cement industries, the crushers, grinding mill, a separator. Another process is where you separate the large particles and the small particles during the grinding here, right? Then you probably need a variable speed drive as well, okay, in order to control the speed of the separator. And then the cement mill, and then the belt conveyor, the bucket elevator, kiln, which require high performance. The only place where you require high performance control is the kiln rotary drive, and the fans and the blowers, okay, which require variable speed but does not necessarily require a high performance drive systems there. This is another example of showing more detail of the kiln drive. Okay, as I said, there are a single drive kiln rotary or a dual drive rotary. ABB, I think, offered dual drive, where you have a Gus gear, and then you have two pinion, which is coupled to the motor, right, via the gearbox. The speed of the motor is first reduced using the gearbox, and then it is further reduced with the Gus gear and the pinion, right, to a suitable values, and then you control that speed precisely, which I say the load torque depends on what is happening inside that kiln. Can be unpredictable, all right, but you have to maintain the speed. So this is where you cannot use scalar control, all right? You have to use a high performance drive here in order to maintain the constant speed of the kiln drive there. There is a problem if you use two drives, because that two drives has to be synchronized. Okay, there are methods on how to solve. So most of them are using what we call the master follower drive, where the first drive generates the speed and the torque reference, and that generated speed and torque reference is fed to the second drive, right? Which means that the second drive is exactly following the master drive. All right, we call that master follower drive system. There are other methods which is still, in the research on how to control, on how to synchronize that drive system. All right. You're halfway there, almost finished. Because this is going to be heavier, okay? the modeling and the control, I cannot go easier than this, all right? But I will try, because when I try to go easier than this, then you might probably will not be able to understand, but bear with me, all right? Because this modeling and control of the induction machines for high performance applications, I normally took what, I think 6 hours of, yeah, of the course in electrical drives to finish that on the modeling and on the control. But here we are just going to finish it within half an hour. So you can imagine the compression there. All right. We're going to talk, as I said, depending on the time. Probably we're just going to go through the DTC, I think. All right. But you can go through the slides and look at on the other two types of control, FOC and PTC as well. Or you can always ask me via emails if you are interested in knowing more of the FOC and PTC. All right. So this is the we're going to look at on the modeling of the source inverter, or VSI, a three-phase voltage source inverter. Again, this is showing a typical drive applications with a diode rectifier at the front end converter there. And then we have the DC to AC conversion, which is what we call the three-phase voltage source inverter. Okay, so this is the three-phase voltage source inverter. And how do we control that? Let's look at more closely here. Instead of connected it to the output of the rectifier, I'm just connecting that to the voltage source here to represent that basically a DC voltage there, okay, which is basically obtained after you filter that. You're going to have a filter here after the rectifier control here. The low voltage will contain ripples, but normally use a filter, large capacitor and inductor to filter out that ripples. So basically you will maintain a stiff DC voltage here, right? So I'm just going to replace that with just a DC voltage there to represent that, right? Because we are going to focus on that 3 inverters there, all right, on how we can control to obtain the variable voltage there, all right? As I said, these semiconductor devices with an anti-parallel diode connected across it is operated as a switch, which means that it is either on or either off, all right? There are two ways of how to control that, to have a variable voltage and variable frequency at the output, modulator or PWM, and without using the pulse width modulator. Okay, both in FOC, we use the modulator, right? DTC and PTC, in some cases of PTC, we don't use the modulator, but we control directly the VSI, which means that if we control directly the VSI, then you don't need a modulator. You control directly the states of these switches here. So instead of the semiconductor devices, I'm just going to replace that with a switch, okay, to be more clear. So the semiconductor devices is operated either as on or off, all right? And using a pulse width modulator, then obviously you need a modulator, which is a power PWM there. Okay, you have an input reference voltage, in which the voltage that you want for the three-phase VA, VB, and VC, the asterisk there stands for the reference value. And then you fed that to your pulse width modulator. The pulse width modulator will generate the suitable switching signals to control the 6 devices. All right, inside there, which is the 6 switches. It will take another 1 or 2 hours in order to explain that in detail. I'm just going to skip that and then just show you the output, what is going on there, right? So this is the output, for example, with a different amplitude of the voltage, but the same frequency, all right? You can see there's no difference between the 3 waveforms there, but if you look closely, there is a difference there. The width of the pulse is different, okay? The width of the pulse here is larger, whereas here is smaller, and here is the least width. All right, which means that this will produce an average voltage with the highest amplitude, lower amplitude, and lowest amplitude. All right, you might say that this is not an AC voltage, it's a waveform with a square, combinations of square waveforms there, but it is actually, you will not see that as an AC voltage, but the motor will see it as an AC voltage. Okay, because the induction motor will basically operates as a filter. Okay, the resistance and the inductance of the motor will filter out that high frequency switching here, which means that the current of the motor will be sinusoidal. All right, it will just remove the harmonics, higher harmonics contents, and we'll just see the motor or see the supply as supplying a sinusoidal current. Current is important because the current is responsible for producing the torque. You know, if you have a ripple in the current, then you have a ripple in the torque. All right. So we try to minimize that ripple by increasing the switching frequency of this inverter. There are two types of inverter, which is widely used in industries, which are the sinusoidal pulse width modulation, SPWM, and the space vector pulse width modulations, which is more and more, I think nowadays are using the space vector modulation pulse width modulations. Again, it will take you, two or 3 hours to go into details of that. So I'm not going to go into the details of that. Now, how do we control the frequency then? You just control the frequency, all right? You just control the switching such that the output voltage will produce different frequency here. The top one is the higher frequency, lower frequency, lower frequency, higher frequency, and the highest frequency there, all right? So the shape of the pulse width modulated waveforms will give you the, some the indications on how the frequency is, and the width of the pulse will give you the indications of the magnitude of the voltage. All right. So if the reference here, for example, is VA, VB, and VC, which is coming from the controller, doesn't matter whether it is from the FOC, for example, or from the PTC with modulator, then the task of this PWM is to make sure that the fundamental component of that voltage follow the reference voltage there. The fundamental component, because this voltage contains harmonics, see, but the fundamental of that voltage will make is going to be following that reference voltage here. Yeah. The fundamental is important, as I said, because the current will based on the fundamental component. Okay, the current will filter out the harmonic high switching frequency and will only see the fundamental component of the voltage. An application, for example, in FOC is that instead of controlling the voltage, you can construct a current loop here to control the current. All right. So this is the VSI that we have seen before. We have a 3 reference voltage here with a pulse width modulator, specifically inside this block here. We have a 3 reference voltage here, but we want to control the current now. We don't want to control the voltage. All right. So what we can do is we can construct a loop here of the current. Okay. We sense the current here. As you can see that we only sense 2 phase current, because the third phase can be constructed if the induction motor is the neutral of the induction motor is isolated, then the third phase can be constructed from the 2-phase current. And then we transform that ABC current into a DQ, 2-phase current. All right. And then this ID and IQ, which is coming from the controller, okay, is compared to the actual current, which is sensed here, which is sensed by the sensor here. Okay, which is typically a Hall effect sensor, and then it's fed to the PI controller, right? And then before it is implemented to the PWM, then you have to convert that DQ again to ABC. All right, now PI controller does not work where you have a moving reference, because if the current reference is sinusoidal, then there will always be a steady state error between the actual and the reference current, all right? We call that moving reference. So in order to avoid that, you transform that AC components into a DC components. This is where you use the frame transformation. All right, getting more and more complex now. If you transform that AC current into using that synchronous into a synchronous reference frame, then your current will be seen as a DC quantity. All right, and PI works well with DC. Right, we'll give a 0 steady state error. So therefore, which is the reason why we have to have that ABC transformation as well as the frame transformation in order to implement that PI control. Now the research on how to implement instead of using PI controller, for example, you can use a fuzzy logic controller and other type of non-linear controller. All right. So this is how the VSI is used to control the current. We call that a current control VSI using PI controllers. There is another, which is typically used in FOC. There's another way of controlling the current using the hysteresis comparator, or it is called a bang-bang control, right? Where the hysteresis comparator will produce either 1 or 0, depending on whatever the state of the error here, right? For example, if your reference is higher than your actual current here, then you produce a positive error here, then your output will produce 1, which says that you need to increase the current. Okay, so the upper switch of leg A is going to be turned on to increase the phase A current. And then once it reaches a certain level, then your hysteresis controller will go 0, which simply means that you need to reduce the current. All right. So it is a bang between the two hysteresis band, which is the reason why it is called a bang control, to control the phase current of each phase of this VSI. It to control compared to the PI because you don't need to linearize the model of the induction machines in order to properly design the controller, because this is a non-linear controller. The hysteresis or the bang controller is a non-linear. You can just design that based on this simulation. However, disadvantage of using this hysteresis, it produce a large ripples in the current, meaning that you produce a large torque ripples as well. All right. So a lot of research is going on. We have published a few papers on that as well, on how to reduce that ripple due to the hysteresis controller. All right. So this is a current control VSI using hysteresis. There are two types, hysteresis and PI controller. But the most widely used in the industry, I'm sure, as well as for ABB, which is based on FOC, I think they use in the industries, they prefer the PI controller, right? Rather than hysteresis. But if it is a direct torque control, then you will use the hysteresis, which is a different concept, but the same using the same controller, which is the hysteresis controller. Talk about that later. All right. So without the pulse width modulator, also you can control the voltage without using the modulator. Okay. How do you do that? You directly control the state of the switch here. All right. There are 3 legs here, and there are 2 times to the power of 3 possible configurations of the switch. All right. Which means that there are 8 possible configurations of the switch. You cannot turn on the upper switch of leg A and at the same time turn on the lower switch of leg B. Why? Because that will cause a short circuit of the supply. All right. So when you turn on the upper switch, then you have to make sure that the lower switch is on. When you turn on the lower switch, then you have to make sure that the upper switch is on. All right. So if you have 3 legs, then there are 8 possible ways of controlling that. 1 refers to the switch when the upper switch is on, whereas 0 is referring to the lower switch is on. Okay. So you have 1, 0, 0, 0, 1, 1, 1, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1. All right. For example, if it is 0, 1, 1 here, is that the lower switch is on of leg A. This is on, and this is on. All right. By doing that, you can directly control the vectors of the voltage, of the output voltage, which is fed to the induction machines. And it can be shown that this voltage vectors is given by this equation here, which gives you in terms of the switching states SA, SB, and SC, which can be either 1 or 0 in terms of the DC voltage there. A is just a unit vector which represents the 3 phases which are separated by 120 degrees from one another, right? So vectors is a complex number. So these are complex numbers, right? When we do the modeling later on, we'll see that that complex number or that space vector. This is used in DTC, all right? DTC and PTC, and in FOC, they use this type of control where you use a modulator. In FOC, you use a modulator in order to control that VSI. Okay. All right. So we know how to control that, right? We know how to control the VSI, whether using a modulator in which you give the reference, or directly control the switching states where you implement the voltage vectors directly by manipulating the switching states of the 3 legs A, B, C. Let's look at on the modeling of the induction machines. All right. this is going to be a dynamic model. We have to use a dynamic model because we want to control the transient states of the induction machines. All right, we cannot use a per phase equivalent circuit that you probably have seen that before in your undergraduate course. Right, that per phase equivalent circuit is only valid for steady state conditions of the machines. If the voltage or the frequency varies during the transient state there, during the transition from one frequency to another, then the per phase equivalent circuit, which is a steady state model, is not valid. That can only be described using the dynamic model of the induction machines. And the modeling of the induction machines here, which is using the mathematical model, is very complex. The reason is that you have a magnetic coupling between the phases, all right? Between phase A, phase B of the stator, there is a magnetic coupling, which means that if you control the voltage of phase A, then a magnet, which is a magnetic coupling, flux which is produced by phase A is going to be affected phase B and phase C through the magnetic flux, right? Which means that you cannot independently control phase A and assuming that it will not be affecting the voltage of phase B and phase C. It will be affected because of that magnetic coupling. That is between the stator phases. And then we have a magnetic coupling between the rotor phases as well as the rotor phases and the stator phases. So the equation is going to be very, very complex with this magnetic coupling. For example, if I write down the equations of the stator voltage and then the squirrel cage induction machines equations here, this is the voltage, the vectors of ABC. And then we have RS, which is stator resistance of the stator. And then we have the current vectors here, IABC. This is not just a scalar quantity. This is a vector, right? And then this is the rate of change of the flux linkage, the phases. Because when you have a flux linkaging the other phases due to the variations in one phase, then you will induce the voltage, right? Then you have to include that voltage into the equation, which is the reason why we have this. All right, on the rotor equations, we have zero voltage because we are not supplying the rotor. Okay, the rotor is obtaining the supply or the power through the inductions, which is coming from the stator, right? So again, this is the stator voltage, stator current resistance, and then we have the rate of change of the flux linkage, which is according to Faraday's law. If you have a rate of change of the flux linking, then you're going to induce a voltage, right? So if I write down the equations of this, then I will end up with something like this. If I expand that, then I will have this is the stator voltage, the stator current, rotor current, rotor voltage, which is 0 for squirrel cage. And then we have a bunch of mutual inductance and inductance there, right? Which is based on that. Okay, and that equation's there. All right, and then we have the stator current and the rotor current there, right? Now, if you look closely there, then you have two set of mutual inductance there, which is what is shown here is LAB, LAS, LB, LCS, and so on there. And also here we have the ACS, CR here. For example, if I take this one, LAS, CR, which is P is a derivative operator, which represents that derivative there, is a mutual inductance between the phase A of the stator and phase C of the rotor. All right. Similarly, if you look here, BSBR, for example, is the phase voltage between the phase A of the phase B of the stator and phase B of the rotor. Here we have also AR, BS, BS, BR, BS, and so on, which is the mutual inductance between the stator and the rotor phases. And then we have the self-inductance here, the stator and the rotor. What is not a good thing about this is that the mutual inductance depends on the positions of the rotor. You know, at a different position, you have a different mutual inductance. It is not a constant here, okay? The LAS, LCR is not a constant. It depends on the positions of the rotor. And how are you going to control that? Very, very complicated. You will end up with a huge number of equations, which is very difficult to model using the three-phase system, which is the reason why we transform that three-phase into a two-phase equivalent system, all right? If you do that, then you remove the magnetic coupling between D and Q, because now the D and the Q is 90 degrees. And if it is 90 degrees, there is no magnetic coupling. All right. So between the phases of stator, you have D of the stator, Q of the stator. There is no magnetic coupling. And on the rotor, you have D and Q of the rotor. You have no magnetic coupling, so you can remove that. You know, the mutual inductance of the coupling between the stator phases and the rotor phases. But there is still a magnetic coupling between the stator and the rotor, because the rotor is still rotating. Okay, we only remove the mutual inductance between the phases on the stator and the phases on the rotor. But between the stator and the rotor, there are still magnetic coupling. Now, how do we remove that? Okay, we can do that by transforming the rotating reference frame of the rotor into a stationary reference frame. All right, or by transforming both frames of the stator and the rotor into the same reference frame, which means that relatively the stator will see that the rotor is not moving, and the rotor will see the stator is not moving. So what happened to the mutual inductance between the stator and the rotor will be constant. All right, it will be constant. So this is where the frame transformation involved here, from the rotating frame into a stationary frame of the rotor. Then if you move the frame, both move at the same frequency, then you will see no magnetic coupling. This is basically virtual. Everything is mathematics. Physically, the stator and the rotor is still there. You see, the rotor is still rotating, you know, three-phase, everything. This is just mathematical model of the system. All right. So it does not physically exist. All right. So it's just a modeling on how we model it in order to derive the controller later on, in order to remove the coupling, so that makes life easier for us. All right. So if you complete the model, which I take, 6 hours of courses in order to completely develop this model, then you will end up with these 4 important equations which describe the model, the dynamic model of the induction machines. All right. The voltage and the currents are all vectors. They are space vectors. It's not just a scalar quantity. It is vectors. All right. These are vectors which represents the three-phase quantity in terms of the vectors. And then if you can actually transform that into a two-axis transformation, because a vector will contain a real and imaginary. So each vector has a real and imaginary, and if you expand that vectors, then you can end up with a matrix equations here, which also represent dynamic model of the induction machines. As you can see here, that the model is basically non-linear. All right. Why it is non-linear? Because you have the speed there. You have the omega r there, which change with time. All right. Unless you are talking about a steady state conditions where the speed does not change with time, then this non-linear model is transformed into a linear model. All right, which agrees our steady state model, which I said earlier. You know, when you studied in your undergraduate, you are concerning with the steady state model in which the speed does not change with time. In that case, then this dynamic model is transformed into a steady state model, which is basically a linear model. All right, but whenever the speed changes with time, then this model becomes nonlinear. On top of that, the inductance is also nonlinear. Okay, if, for example, it depends on the saturation level of the flux in the machines there. But in most cases, we are going to assume that the inductance are just a linear constant values. All right. So, and also we can also develop the torque equations here, which is the dynamic torque equations here, in order to describe a complete model of the system of the induction machines. Okay. So using these 4 equations combined with the torque equations here, this is how, this is where we can develop the field-oriented control and the direct torque control. All right. I have to use this equation in order to describe FOC and DTC, right? And as I said, to develop this model is not going to be straightforward. It will take time sometimes, but here I'm just finishing it within just, I think, 15 minutes. Okay. So what is the character of the high performance motor control before we go into details of the FOC, DTC, and PTC, which we have time. We finish at what? At 1, is it? 11:30? 12:30, right? 30 minutes more. All right. I'm going to speed up a little bit now. All right. So, all right. What is the high performance motor drives? Where you need to control the speed and the torque and even the position precisely in some robotic applications, for example. And that requires fast dynamic response and good steady state response, which is basically zero steady state error. To achieve this in the DC motor, as I said earlier in the talk, is that it's easier because in DC motor, you can do this very simple by just maintaining the field flux and controlling the armature current here. All right. This is DC motor. And that DC motor, the armature current can be controlled for using a simple power electronics converters, not as complex as the three-phase VSI there. But you can control that. If you control the current here, then you can directly control the torque, because when you control the current here, then you don't affect the flux, because the angle between the torque and the flux component is 90 degrees. It's always 90 degrees, right? Remember, when it is 90 degrees, then you have no magnetic coupling between the two, right? And how do we obtain that 90-degree separation? By brushes and commutator of the DC machine, right? I'm not sure whether you understand that, but if you have studied DC machines before, then you know what I'm talking about, which is the brushes and the commutator, which maintains the positions of the torque and the flux component of the DC machines, which make the control a lot easier. Now, for induction machines, it's not going to be straightforward, okay, because the source on the rotor is coming from, and as I said, the coupling between the two cannot be avoided. All right. So in order to transform the induction machines into the form which is similar to the DC machines, then this is where we introduce the field-oriented control. Okay, as I said, which was invented in early 1970s, which most of you did not exist yet. Okay, I'm, kids during the time, right? This is where the a turning point of the motor drives applications, where the AC motors can be used for high performance applications using the field-oriented control. All right. So in order to do this, we have to write the torque equations in terms of the rotor flux and stator current. All right. So we start off with the stator current and rotor current here. IS there stands for stator. IR there stands for rotor current. G there is a general reference frame, which can be any frames which is rotating synchronously, both with the same speed of stator and the rotor. All right. P is the number of poles. LM is the magnetizing inductance, and IM there stands for the imaginary part of that multiplications of the two vectors. All right. And the S3 there, it stands for the conjugate of the vector. All right. So in practice, obviously, we cannot measure the rotor current because it is, especially when it is a squirrel cage, then it is impossible for us to know what the stator current is. So we have to remove the rotor current. Okay, so we have to remove the rotor current using the rotor flux linkage equations that we have developed earlier. If you substitute that into this equation here of the rotor current, then you will end up with the new equations here. All right, so if you multiply a vector with its conjugate, it will not contain imaginary part. Okay, so which means that I can now reduce the equations into equations here, which is simply a multiplications of the stator current and the conjugate of the rotor flux. Because when you multiply the stator current and its conjugate, then there is no imaginary part. Whereas in the torque expressions here, IM there stands for that we just want to take the imaginary part of that multiplications of vectors. All right. So if you expand that, the stator current and the rotor flux conjugate, then you end up with these equations here. Right. So what that equation stands for, in a stationary reference frame, for example, I have two vectors here, stator current vector and the rotor flux vector. All right. In the stationary reference frame, I will resolve these vectors into its D and Q component. The stator current will have a Q component. The rotor current will have its Q component. The stator current will have a T components and its Q components, and the rotor flux will have its Q component and D components. right? If you resolve that to a stationary frame, then this is what does it look like, right? In that equation, psi RD is there, which is the D component of the rotor flux in projected to the D of the stationary frames. And then psi RQ is where you project the rotor flux into its Q component stationary frame. Similar to the, we have that. Now, the only thing that we can control is the stator current. So if I change the SSQ here, for example, here, then I will also affect the rotor current, the rotor flux component, Q component. And if I change only S, there's another component here, ISD, then I will also affect the D component of the rotor flux, which means that if you look at this equation here, if I change ISQ, then I will also affect this. Okay, if I change ISD, then I will also affect the IRD there, which means that there is no coupling, there is no decouple between the torque and the flux component, which is different from what we have in this DC motor. In DC motor here, the torque equations there, K is represent a constant, flux is the field flux on the stator, and IA is the armature current. You can control the torque by just, as I say, controlling IA without affecting the flux. But here, if you change ISQ, then you also change IRQ, which is not good, all right? So what we do is that we define a new frame here, which is attached to the rotor flux. All right, if you attach the frame to the rotor flux, then there is no Q component of the rotor flux. Look at the equations here. There is no Q component of the rotor flux, which means that I can now replace the torque equations here with a new equation, torque equation here, which is just simply given by that. All right, there is no Q component. You look at here. Oops. This is a previously equation, torque equations now. Now I remove that term there. So I remove that term there because there is psi RQ is 0 here. If you project the flux to its rotating frame, then, and if you align the axis to the rotor flux, then obviously there is no Q component of the rotor flux. All right, so which means that you can remove the Q component in the torque equations there. Then you end up with just a simple equations here, where the rotor flux D component is equal to the magnitude of the rotor flux. All right, and the stator flux component here remains as it is, which means that now I can change ISQ without affecting the flux, which is similar to what we have in the DC machine. All right, so which means that I can have a fast and quick torque control of the DC AC machines, provided that I transform everything into a frame which is rotating synchronously with the rotor flux, which is the difficult part of the algorithm. All right, because in order to do that, you have to know what is the angle of the rotor flux, right? And then if you know the angle of positions of the rotor flux, then you can transform the stator current into these rotating frames, which is rotating synchronously, which means that in these rotating frames, the current is seen as DC because it is rotating together with the vector, okay? You see, this frame is rotating synchronously with that current here and with that rotor flux there. So it is rotating together, which means that what is seen in this rotating frame is a DC quantities. So in order to implement that, then you have to know the flux position. There are two ways of obtaining the flux, rotor flux position, the indirect and the direct FOC. In the industries, most of the methods use the indirect FOC, where you measure the speed or you estimate the speed in order to obtain the rotor flux positions, all right? So how do we do that? Well, we have to go back to the rotor voltage equations in the rotor flux reference frame, all right? In the rotor flux reference frame. And again, I have to remove the rotor current in terms of the rotor flux here by using the rotor flux linkage equations. I remove that IR there with this rotor flux in terms of the rotor flux and the stator current. I will end up with that. And then in the reference frame, which is attached to the rotor, then you can see that the difference between the speed there is just simply a slip frequency, okay? Because the rotor is rotating at a synchronous frequency. This is the speed of the rotor. So the difference between that is a slip. And the magnitude of the rotor flux in the rotating reference frame, it just equals to magnitude of the rotor flux, the d-axis of the rotor flux, okay? There is no q-axis, which means that you can separate the d and the q component of these equations, and then you can implement that using the three equations that we have here. All right. The first equations, which is derived from the rotor voltage equations, will give you the reference of the stator current. Okay, the star again is representing the reference value. And then the second equations will give you the Q component of the stator current. And the third equations will give you the slip. All right. So which means that to implement that, then you have the torque and the rotor flux reference, all right, which basically constant as long as it is below the base speed. Then from that reference value, you generate the D and Q component of the rotor of the stator current, okay, using the three equations that we have just derived just now. And then using the measured voltage or the estimated, sorry, the measured speed or the estimated speed, you add that with the calculated slip to produce the rotor flux speed. You integrate that to give the rotor flux position. And then from there, you transform the rotating frames here into a stationary reference frame. And then you transform back to a three-phase quantities, and then you implement that using the current control voltage source inverter. All right. If you look at closely to this structure, it's like a feed-forward structure of the control system. It's not a feedback. Okay, it's a feed-forward structure, which means that a feed-forward structure has the characteristics of highly sensitive to parameter variations, parameter mismatch, right? Which means that whatever, when you run the motor for quite some times, then the actual parameters will vary from the actual, the model parameters that use in the model. There is a parameter mismatch there, which will, degrade the performance of the drive system. A lot of, research has been conducted in order to improve that mismatch parameters between the actual parameters and the parameters used in the model, especially when there is a variations in the temperature when you operate the machines for quite some time, right? So you have a rotating frame on left-hand side, and then you have a stationary frames on the other side. This is just a DC quantities, whereas this is the actual quantities. And everything here is implemented using the digital signal processor. The sampling can be very, very high, can be very small, in order of few, maybe 20 or 50 microsecond. Okay, for every 50 or 20 microsecond, you have to produce the reference value of the stator current D and Q inside your microprocessor or digital signal processor. I think we only have time for direct torque control. We don't have time for the PTC. Okay, we're going to go very quickly on the direct torque control. I should have start with direct torque control rather just now, rather than start with the FOC, because direct torque control is more relevant to what you have at PT segment. Okay, all right. It is a simple control, all right, compared to the FOC, because you don't need the frame transformation here. You can see the structure here. It's very simple. You have a pair of hysteresis comparator, and then you have the torque reference, and you have the flux reference, which typically kept constant, as long as it is below the base speed. And then if it goes beyond the base speed, then you reduce the flux inversely proportional to the speed, right? And then you have the voltage vector selectors, in which you directly control the switching states based on the demand of the torque and the flux, right? Which is coming from the hysteresis comparator here. Then from there, that voltage vector selector, which is just simply a lookup table, is fed the voltage source inverter to control the three states of the phases there, right? And then how do you estimate the torque and the flux? You just measure the current and you just measure the DC voltage, and then you can estimate the voltage and the flux. Very simple. You don't need a frame transformation here, all right? You don't need a current controller. You don't need a modulator. You just need a lookup table a pair of hysteresis comparator, and an estimator here. That is the simplest form of DTC. But nowadays, of course, there are variations to this, which complicates things, right? Instead of using the hysteresis, you have a PI controller. Instead of implement that in a stationary frame, you implement that in rotating frames, and you require frame transformation and so on and so forth. But when it was first introduced, this is the structure. Then it evolves over, so after a couple of years, a couple of decades, into a more complex systems. Now the problem is, how do we select the voltage vectors in order to control the torque and the flux? Right? We start off with our stator voltage equations, which we have the model, we have derived the model. We've seen how it is derived before. The rate of change of the stator flux linkage is equals to the Vs minus RSIS. These are all vectors, right? The bold letters represent the vectors. It's not simply scalar quantities. Now, if I assume a negligible ohmic drop in Rs, then I can assume that a change in the flux is just simply equals to the voltage vectors times a small change in the time, right? This is also valid if the small change in time is very, very small, which means that I can control the change of the stator flux by applying a voltage vectors for a small period of time, right? And there are 8 possible voltage vectors that I can do that, right? So for example, this is again the model that we use in the DTC. Okay, we control that directly, okay, by selecting one of the 8 voltage vectors here, so that we can control the locus of the flux, of the stator flux, right? For example, if this is positions of the flux, or the conditions of the flux, the vector of the flux, xt plus 1, then if I apply V4 there for a period of time delta t, then the flux will move to a new position. All right. Then after that, if I apply another vectors V5 for delta t, then a new flux will produce a new flux at different position. So if you combine that in a very fast time, okay, for a very small period of time, then you can actually see that the flux is actually moving according to what we control, okay, by selecting the voltage vector. Now, in order to maintain a constant flux, then the circular of the vector of the flux is going to, the locus is going to be circular. All right, so we have to make sure that the flux follow the circular locus to maintain the magnitude of the flux constant. And we do that by defining the hysteresis of the flux. All right. For example, if I detect a positions of flux in sector 1, then I can control the flux in sector 1 by choosing V1 and V2. So if I want to increase the flux, I use V2. If I want to reduce the flux, then I use V3, right? Then if I move to the next sector, then a different set of voltage vectors has to be used in order to control the flux. Okay, now I'm using V3 and V4. If I'm in sector 3, then I'm using V4 and V5. If I'm in sector 4, then I'm using V5 and V6 and so on, right? If I'm in sector 6, obviously, then I'm using, if I'm in sector 5, sector 6, then I'm using the V1 and V2, right? V1 and V2, go back to this. So which means that in general, if you are in the K sector, then you use K plus 1 vector and K plus 2 vector to increase and respectively, right? So that is how you control the flux. But remember, at the same time, we control the flux, we have to control the torque because we are using the same lookout table. So how do we control the torque at the same time? We have to go back to the torque equations, which defines the torque in the stator flux and rotor flux magnitude and delta SR in terms of the angle between the two. All right. So this is not a vector here. Psi S and psi R is not a vector. It's a magnitude of the stator flux and the rotor flux. Right. So remember, when we control the flux circularly, then we maintain the magnitude, which means that here, psi S is basically just a constant, all right? Because within that hysteresis band, provided that hysteresis band is very much smaller than the magnitude of the flux itself, then we can assume that, you know, if we maintain the circular locus of the flux within the hysteresis band, then the magnitude of the state of flux is just a constant. All right. Again, and another thing that we have to look at on how the state of flux and the rotor flux varies. The rotor flux will follow the state of flux according to a equation here, which basically gives you a relationship of which says that the rotor flux is lagging behind the state of flux with a low pass filtering action here. That is basically just a low pass filter transfer function there. Okay, P is the derivative operator. Sigma is the total leakage factor. Tau R is the rotor time constant, which is equals to LR over RR. Okay, so we control the flux using the voltage vectors, which means that the motions of the state of flux is going to be jagged. You know? But because of these equations which show here, the rotor flux is going to be smoother. It will remove the high frequency motion of the state of flux, which means that the rotor flux will be following the state of flux behind with a smoother motion. All right, according to that equations here. Now we can exploit that. For example, shown here is the stator voltage, the stator flux and the rotor flux, which is moving synchronously together. But when I, at a moving reference frame, but if I, for example, case one, I select a voltage vectors to increase the stator flux, then what happened to the angle here? The angle will increase because the rotor flux will not immediately follow the stator flux, but it will be lagging behind. Okay, the instant you change the stator flux by using a voltage vector, the angle will immediately change, which means that you are immediately increasing the angle, which means that you are immediately increasing the torque here. All right. Now I can increase the stator flux here, and at the same time, I can increase the angle here, which means that I can control the torque as well. Or I can reduce the stator flux, for example, by using a voltage vectors in that directions. But I can increase the torque because the angle is still increased. All right. Increase in the flux, increase in the torque, reduce in the flux, increase in the torque. Which means that by selecting one voltage vectors, you can control the torque and the flux independently within the hysteresis band. All right. There is one possible. Then if you choose a reverse active voltage vectors, then you can either increase the flux magnitude if you use that one, for example, or you use a vectors that which is showing in that directions, then you are reducing the magnitude of the stator flux. But at the same time, you reduce the angle. So if you reduce the angle, what happened to the torque? The torque will reduce. Yeah, the torque will reduce because the sign of angle is reduced. Okay, so the sign of angle reduced, which means that the torque will be reduced. So by using this, you can reduce the torque, but you can also increase the flux, and you can reduce you can increase the flux. Okay, so we have a choice, and the third one, which is what we call the zero voltage vectors. You don't do anything to the stator flux. All right, because zero voltage vectors will not change anything. You know, V is equals to 0. Then the stator flux will not change, but the rotor will keep on moving. All right, closer to the stator flux, which means that it will move slower, slower rate. The angle will be smaller, which means that the torque here is going to be reduced. All right. So there are three ways of controlling the torque and at the same time controlling the flux. Increase the flux, increase the torque, reduce the flux, increase the torque, or you can reduce the flux, increase the torque, reduce the torque, or increase the flux, reduce the flux. Reduce the torque. All right. Or you can maintain the stator flux constant, but reduce the torque. Okay, which is the last one here. And if you do that, then you will end up with a lookup table. All right, because this hysteresis will define you whether you need to increase or reduce the torque, and this hysteresis will define whether you need to increase or reduce the flux, and that is fed to a lookup table, which is shown here. Okay, depending on the stator flux position. Remember, we have to define that which vectors to use based on the positions of the stator flux. All right. So we still need, so there are 3 index to the lookup table: the torque status, the flux status, and the positions of the state of flux. And we construct that, we will end up with a lookup table, which is something similar like this, which means that we can control the torque and the flux independently within the hysteresis, band. All right. So I don't think I have time to go through the predictive torque control. Anyway, it is a relatively new control, which I don't think is commercialized yet at the moment. People are still working on this, on how to convince the industry, because industry will normally take more times to be convinced. They don't want to change to something new if it is not proven yet. All right. So the research is still going on the predictive torque control, which is relatively new. So I don't have time to do that, but you can always have a look at this, and then you can ask me anytime if you want to know more about this. What I want to do now is to go on what we are basically very quickly on how, what we have implemented in our lab. This is the picture of my lab, which is what we call the UTM Proton Future Drive Lab, which is a satellite laboratory. Previously was a satellite laboratory of the Proton, but now they changed it to EV lab because Proton has, changed the policy. It was taken over by Geely. I don't know whether you know about that. So it is no longer sponsored by Proton in the lab, and we call it EV lab. But this is anyway the picture of that. So what we have implemented in the lab is the 3 control structure there: FOC, DTC, and PTC. We have done that using a simple setup here. This is a 3-phase voltage source inverter. We use a DC power supply to limit the current, to maintain or to safeguard these IGBTs there. We have a gate drivers. We have a DSpace DS1102, 1104 controller, which is interfaced with the PC there. I think Dr. Imran used this setup in your, are you using the DS1104 in UTM? Yeah, it's still there. We have more DS1104 in our lab now. Yeah. All right. So control algorithm that we have implemented, which I'm going to show you, is FOC, DTC, and PTC, where all the algorithm of estimating the torque, the flux, and the flux position, as well as controlling the torque and the speed, is implemented within that DS1104, including the blanking time here. All right. So, and then we have the interface with the DS1104 using control desk software, which is provided by DSpace. Now we have the incremental encoder here, IE, to sense the speed. Okay. We also have research on predicting the speed, which I'll show you later on. And then we have the current sensors here, and then the motor is coupled to the load. So in order to program the DSpace, which is shown here, you have where you slot in the PC slots of the of your PCI slots, which is contain 2 processors: the main processor, the master processors, and the slave processors. The master processors using the MPC 8240 there, which 64-bit floating point digital signal processor. And then we have the slave, which is implemented using the Texas Instrument 320F, 240 digital signal processor, running at 250 megahertz, the main processor. Then we have several ADC, analog to digital and digital to analog converters, programmable digital, and then the into incremental encoder interface. You can program using 2 ways. You can develop automatic C code generation using Simulink, which is not fast enough for our applications, unfortunately. Okay, because it is not optimized. So the option is to directly program that DSpace using C codes. That is what we do in the lab. For example, if you implement DTC using Simulink, the sampling time, the lowest you can go is around 50 microseconds, which produce a very large ripple. And if you do a hand code written C codes, you can reduce that to 35 microseconds, right? Which is a significant difference there. Now, the experimental setup, just one example, which is basically the same for all control techniques. You have the IGBTs here. You have the current sensors. You have the IGBTs, 3-phase VSI. Then you have the gate drivers, and you have the DS1104 interface board, which is not shown here. This is the interface cable, which is slots to the PC there, right? This is where you connect to the three-phase induction motor, where you have the hysteresis load to control the load of the induction machines. All right, so this is the basic setups of the drives control system that we use in our lab, and it is applicable to all control drive systems. The only thing that we need to change is the algorithm. All right, PTC, DTC, FOC use the same setup. The only difference is on the control algorithms. Yeah. So this is the result. That's on the scalar control, and I show the results anyway. You see, this is the speed. The first one is the speed. This is the torque, and this is the stator current, phase A. All right. You can see that for the scalar control, I'm reversing the speed from minus 700 RPM to plus 700 RPM in how many seconds there? 2.5 seconds. Take long time to reverse the speed if you use scalar control, right? Which is good for application which does not require that, fast. 2 seconds is good. It's fast enough if you control the speed of a pen, for example. All right. You don't need a precise or faster control. But if you control the torque, the speed, reversing the speed there from minus 700 RPM to plus 700 RPM, you can do that in just less than 1 second using the high performance control, for example, your FOC, DTC, and PTC there. You cannot see the difference in the torque there because it's looked very, very fast there, the rise of the torque there. But if you zoom to that, this is actually the experimental result, okay? If you zoom that, you can see the difference between the three, which means that PTC gives you the fastest response, which is shown by the black threads there, okay? Compared to DTC, which is in red, and FOC, which uses modulator, is in blue, okay? If you use modulator, then you slow down the implementation process, right? Because there will be delay in the control systems when there is a modulator, which means that DTC, PTC does not require modulator, removes the delay, it gives you a faster torque response. Right, that's just a summary of that. We have, over the past decades, since 2000, early 2000s, we have done a lot of research in direct torque control, and we have published several papers on the IEEE transaction. You can see there my PhD work in 2001 in the IEEE transactions of industrial applications, where I improved on the stator estimations. Then I maintained the constant switching frequency with the help using the constant switching frequency controller. I removed the hysteresis, replaced the hysteresis with constant switching frequency, and we managed to publish that in 2 transactions. And then we improved the constant power region, which is the overmodulation region of the direct torque control. Managed to publish that into 2 transactions. And then we also estimate the speed using the extended Kalman filters, as well as we have published that in the powertronic transactions. And we also have improved the hysteresis DTC by adjusting the lookup table to remove the flux loop, the flux droop, we call it the droop. And we managed to publish that in the IEEE transaction industrial informatics as well. There are several other transactions which are not listed here. Currently, at the moment, I have 2 PhD students. If you are interested, but you still have a long time to go. Still have a long time to go. You can join us if you want to, to work on this model predictive control. And we are working right now on the applying the MPC, model predictive control, for the hybrid energy storage system for electric vehicles. Instead of the battery, you use a supercapacitor in order to remove the stress of the battery. And we are controlling the supercapacitor current and voltage using the finite control set MPC, right? So that is what we are doing. One of my PhD students doing on that. And also we are removing the tuning factor of the PTC in its cost functions. I also have another student doing on that as well. So I think that will end my presentation. I will get to answer any question if you have anything I can answer. Yeah.